Hi, is this on? Cool. Welcome everybody. Thank you for coming. I'm going to give a brief introduction about me. My name is Billy. I work with Cosmos Network. I've also just finished a lot of work with Eric on Black, a project called Clovers Network. I'm working with Gnosis. I'm the author of the Refundable Token EIP. Built ENS Nifty, and last but not least, the Curation Market Meme Lords. Today I'm going to be talking about batch bonding curves. First I'm going to give you a little background on bonding curves in general. So if any of those words in the title don't mean anything to you, don't worry about it. We're going to talk about front running in general, and then we're going to talk about a solution that I've proposed called batch bonding curves. There's 3 different implementations. We'll go over each one. We'll talk about a little of the documentation, and then I'd like to open it up for questions and discussions. I think I've got a clicker here. So, a little background. Bonding curves are automated market makers. You might be familiar with the term. They're really useful for markets. They provide liquidity. So there's a lot of places where you need liquidity that you don't have it already. One that you might be familiar with are prediction markets. It uses a logarithmic scoring rule for market making, invented by Robin Hanson, an advisor to the Gnosis project. You might be familiar with Bancorp. They have a market maker that uses something called a reserve ratio. There's also Uniswap, which uses one called XY equals K, built by Vitalik Buterin and Alan Liu, again from Gnosis. There's also the slope formula bonding curve, which is the one that's often spoken about by Simon de la Rouvier. I'm going to use the slope formula bonding curve as a sort of frame of reference for today, but most of these are just different ways of implementing the same thing. So with the slope formula, a good way to think about it is you have an x-axis, which represents the total supply of a token, and a y-axis, which represents the price. These are new tokens that come explicitly from one location. They can be minted and they can be burned from this location. This location also accepts some collateral token, like Ether or Bitcoin or Atoms or something like that, something that already has value. It will hold that valuable token and mint these bonding curve tokens. The more tokens that exist, the more the price will be. You can think of it a little bit like supply and demand. Feels unintuitive because usually supply and demand, the more the supply, probably less demand. But because you have this mechanism here that marries those, the demand is sort of attached to the total supply. So the more tokens there are, that means the more of a demand there has been, and so the price should increase with that. Here's a representation of a slope formula that's often given. You can see total supply squared at the top right, that price equals. So this is sort of a quadratic scoring rule. It accelerates to the right. Excuse me. What's really nice about this way of talking about it is that the amount of Ether, say, or Bitcoin, whatever that collateral token is equal to the integral of that slope formula. So you can see all of this blue in here, the collateral reserve. That's actually accurate to how much real money is needed to mint that many bonding curve tokens. And the price on the left will show you exactly what the current price is depending on how many are in circulation. So you come up and you're like, all right, I want to buy some tokens, I send money into this. The collateral pool increases, the token supply increases, and the price increases. You come back and you want to get rid of these tokens, you burn them, you're able to remove some money from that collateral pool, and the price shifts back down. So it's always changing based on the current price and the current demand. Bancorp has a similar implementation. They use this thing called reserve ratio. Probably unimportant, but up there you can see a little bit how you would talk about price, where the reserve ratio comes from, and where the market cap is in that formula. I'm going to move on though. Some example use cases for these would be, again, like I mentioned before, prediction markets. So in a prediction market, you have a bunch of tokens that represent different outcomes. But you have this problem of who's going to buy my outcome token. If you can find somebody to buy it, another person, that's great, but often you can't when you have such a small marketplace, but with a lot of tokens. So it's great to have a market maker who's there willing to buy and sell from you. They use a logarithmic scoring rule just because it makes all the sort of prices add up. But it's also difficult because you have to add money to that market maker to begin with. It's why you have to fund a prediction market often. If you don't do that, you have something like Augur, and you have all these markets out there with no liquidity. Nobody's willing to buy or sell these tokens. So it's nice to have a market maker out there taking care of that. Microeconomies is another one. So there's a group called Grassroots Economics in Kenya. There's a lot of local currencies, but it's hard to trade between these different groups. And so it's nice to have these market makers who will immediately allow you to exchange between these communities so that you don't have this problem of I have token A, but you want to sell it in token B. App-specific tokens. This was the first time that I actually got interested in all these things. I have this project called Clover, as I mentioned earlier, and it's very much experimental game. I have a token attached to it that has a reward mechanism, but I wanted to be able to offer my users the ability to buy and sell this token. Knowing that it's going to be a small pool of users, how do I provide this? Am I going to be matching their orders? There's going to be a huge spread between the buys and the sells if there's not that many people. It's low liquidity. So when I heard that there was a way to sort of bootstrap that market process by providing a market maker, it was really exciting to me. There's all sorts of games that would be like this, though. You just need to offer this service to your customers. You can create a bonding curve to allow it. Also shout out, the Clover's Network project I mentioned will be launching here in Berlin, August 20th, during Berlin Blockchain Week. Stick around for that. Curation markets. This is sort of a wide category of types of applications. It's been defined as anything that has skin in the game metrics. So that actually includes prediction markets where you're willing to put your money where your mouth is about what you think the outcome of something will be. It includes something I've been calling attention markets that I'll get into in a second, and token curator registries if you're familiar with that concept. So curation markets as attention market I think are really exciting and super weird. This is sort of how I think a lot of people understand the stock market working in general. Not that there's like real effects of supply and demand, but it's just sort of sentiment of people like, oh yeah, I think the price is going to go up, so I'll buy it, because they think the price is going to go up. But this is actually sort of doing that explicitly. So the price represents the attention and the sentiment of the asset, but the asset is actually nothing. One example of that would be like trend forecasting. So say there's a bunch of tokens for different types of shoes. I really think that this one shoe is going to be popular. This token has nothing to do with that shoe, except for like we've all decided to let this token represent this shoe. And so people buying and selling these different tokens for these different shoes represents which shoe we think will be more popular at any given moment. It's like a prediction market that never resolves, because there's no way to say, oh, this was the most important shoe or something like that. But you have this ongoing buying and selling, which kind of points to consumers' thoughts about what is the most popular one at any given moment. And so if you're able to sort of buy and sell sentiments, you can maybe perform really well on this thing, but it's just attention. Another example of that is the meme boards app I talked about before. This is similar to Meme Economy on Reddit. It has 1 million users now. People just sort of buying and selling on the perceived popularity of different funny images or something like that. There's nothing that actually marries these images to that marketplace, but as long as people sort of go to this place and talk about it, they can decide this is where these metrics are discussed and carried out through markets. It's more about like buying and selling zeitgeist. Again, token curator registries. This is actually a bit closer to the app example. You need to have these tokens that exist inside these registries. You need to have liquidity for them because it's often very small participation groups. So where should these come from? It also sort of very conveniently sidesteps the ICO phenomenon. Whether that's good or bad for your project is dependent on what it's meant for, but it might look more like a continuous organization instead of one who does an ICO. And continuous organization, it's sort of like having shares that are bought and sold with a bonding curve at an ongoing basis. So that locked collateral could potentially be used for working capital. They could take money out of that collateral pool, and the token holders might receive some rights, like governance, or they might receive dividends, as if they were real shareholders. This is the second reason I got really interested in these. I've been working with Aragon Black, I mentioned, to build these mechanisms into the Aragon framework. And a company called CellBorders is going to be using them to make legally compliant ones. I'll talk more about those right now. Aragon Black was the group that's building the fundraising app, and CellBorders from Thibaut Fabre realized that Regulation C in America actually fits really conveniently into this. They allow you to raise money with unaccredited investors up to, I think, $1.3 million. The big kicker is that they let those people buy and sell the stock back to each other, but only if there's an explicit pricing mechanism. And this fits perfectly into bonding curves because that's exactly what they are, explicit pricing mechanisms. There's also Gnosis and DAOstack have just launched the DEX DAO. A lot of this work was carried out under their guidance in preparation for allowing the DEX DAO to potentially have its own token. So that work is still ongoing in parallel, as well as Giveth working with augmented bonding curves in a semi-capacity. So continuous organizations potentially have this attribute of injecting collateral instead of dividends. It's a really interesting mechanism. We can talk more about it later, but it's maybe better to call it like a buyback than a dividend. But a really convenient way to say reward token holders isn't to say mint a bunch of new tokens with all that profit that you have and then send it out to each one. That would be more like a dividend. You can sort of compress that step of giving them all these tokens by just adding more money to that collateral pool so that all the tokens that exist already, prices mechanism will just increase. That curve that we looked at before just sort of gets pushed up. If you imagine again that the collateral fills the space under the curve perfectly, if you shove more collateral in there, you're going to have to change the curve to accommodate it. So it might move up and the pricing mechanism will increase with it. Similarly, the opposite can happen. If you need to remove some of that collateral for working capital, that collateral will no longer fill the entire curve, so the curve will come down. The price per token will decrease. This is sort of something that you would maybe trust an organization to do because you think they will eventually make profit, put that money back in, a lot closer to a stockholder or something like that. So we were here to talk about batch bonding curves and greeting DEX FrontRunners. That's because all of these bonding curve mechanisms are on-chain, and anything on-chain is susceptible for front-running. Basically, front-running is possible whenever there's a guaranteed price movement. And when you see these transactions coming through, you can guarantee what happens. These are deterministic systems. You can pre-calculate exactly what's going to go. These are also all gathered in a mempool. It's not finalized what the order of the blocks are until the miner actually finishes them, or the validator. So imagine this scenario. You've got a buy order you want to make. I'm a malicious actor. I decide to sandwich that buy order with my own buy order and sell order. So originally it's just a buy order coming in, going to push the price up. And now they see that, they make their own buy order, they give it tons of gas to make sure the miner puts it in front of it. They push the price up, I come, push the price up even further, and they immediately sell. They've just sucked out a lot of the energy from my purchase. They've basically stolen part of my money from that. This is illegal in traditional finance. Alternatively, a sell order. So I want to sell my position a little bit. They see it coming through. They'll sell before me. I'll sell after, move the price even further. Then they buy back again. In doing so, they're able to increase their current position with no risk. So when it comes to the continuous organizations, this is similar to the dividends or the working capital withdrawal. When you are going to, say, give those dividends by injecting collateral, you guarantee that the price is going to move up. So it would be possible for somebody to front run that. If you were going to take money out for working capital, that's going to lower the price. Similarly, someone would be able to position themselves to benefit and gain more from that. So this stuff isn't all theoretical. This is happening in the wild. There's been a lot of writing from Phil Dyan and a lot of his colleagues. There was a great presentation at DevCon 4 called Smart Contract Security, where this image came from and some of this data, as well as a paper they wrote recently called Flash Boys 2. From that paper, they estimated that there was $4,500 a day being made in August 2017 on Ether Delta alone. Similar attacks have been demonstrated on Bancor, and they estimate that 30% of all blocks contain some kind of programmatic arbitrage. So this is rampant, it's happening all the time, and it's only increasing. We have to figure out a lot of these things before we can actually offer any of these DEXs to the public, because there's no way that any customer would want to use the DEX knowing that all of their purchasing power will be watered down by FrontRunners.
If you KYC the people using it, then you probably don't have to worry that much about it, right? Because they'd be committing a crime with their name behind it.
I mean, it's hard to say that just because they purchased right before you and they sold right after you, that it's necessarily malicious. I mean, it could just be that that's their right to do it, But you're right. I mean, there are certain ways you could throw a legal look at it. Some of the other ways that projects have prevented to mitigate it is by adding gas limits onto the transactions. They've also made return amounts. So if I send in $1 and I'm expecting 5 of these tokens back and I only get 4, the transaction might fail. This is a pretty bad user experience though, because I just need some of those tokens, and every time I try, it keeps failing. If somebody keeps front running it, it's just going to keep failing. So, reintroducing batched orders with common clearing prices. I say reintroducing because this already exists on traditional markets, but we haven't seen it yet on decentralized exchanges. The basic idea is that you batch all the orders together and you find a common clearing price. So you get all the buys and sells for some span of blocks, and then you clear them. You calculate the price and you deliver the outcome. There's 3 mechanisms that we've kind of come up with that would do this in different ways. Each of them have different attributes which may be beneficial to your system, maybe detrimental. So it's good to sort of consider each one and when and why you would use it. I'd be really curious about your all's opinions on these different ones as well afterwards to talk about, because I think there's probably some use cases I haven't thought of, and probably also some benefits or drawbacks that would be interesting to go over. First one I'm calling ordered batches. Second one is match and fill, and then the common clearing price. Ordered batches is the simplest one. You basically just decide to reward one party or the other, because when you collect all the buys together, you collect all the sells together, you decide to execute all of them at once, then all the other ones at once. But depending on which one you execute first, somebody's going to benefit over the others. So you execute all the sell orders first, the price is going to go down really low. And that's going to be great for the buyers who are going to buy at a really low price, move the price back up. Alternatively, let the buyers execute first, moves the price really high. Sellers love that because they get a really high selling price, moves it back down. So if you want to, say, reward your buyers, you want more people coming into this economy, maybe that's fine for you. You actually could choose this because you want more people coming into your token ecosystem rather than exiting. This could be a choice you'd make. Alternatively, maybe you really want to reward your sellers, do the opposite. This is again sort of a demonstration of, say, the blue is the starting price, the red would be the execution price after the buys came through that the sellers would want. The green would be the execution price that the buyers would want. The sellers were executed first. Second one is match and fill. This is my favorite one, and this is the one that we've been using on Aragon Black. I have to give thanks to Mark Kopelman from Gnosis who helped me develop this one. So when you have this batch bonding curve, you have a current price. We know that as soon as you start buying or selling on it, that price is going to change with whatever direction you're moving it. But you can also imagine at that moment there is some current exact price. So with match and fill, you take these big groups of buys and these big groups of sells, and you use the exact price to match the orders. You match them until one whole side is gone, because there's always going to be, say, more buying power than selling power, more selling power than buying power. There is the chance it's the exact same, and then you're just done, and that's great. But chances are you have a little left over, and you use that in a normal buy or sell. Then you combine those two prices, find the average, you divvy it up to all the people who put in different amounts of money. Common clearing price is where you would find a uniform price for all the buys and all the sells. This takes some tricky math, which doesn't work very well in the EVM, but it is possible. I have to also shout out Tom Walter for help on this from Gnosis. This at first sort of was what I was hoping for in the long run, but of course it was a more complicated one. And we did figure out a way that it would work even on restrained computing environments like the EVM. But afterwards, I kind of went back to thinking the second one was my favorite because it sort of represents a little bit more of the accurate market. If there are more buys and sells, probably the price should move in that direction. Whereas this one, you have everybody getting the same price no matter what. But if you do want that, the way you would do it is by skipping over all this complicated math and just knowing that it's hard to find, but it's possible, especially off-chain. So what you can do instead is make it easy to verify on-chain. This is again a page out of Gnosis' book from the way they're handling diffusion, their current exchange, which has very complicated computation, but it's relatively easy to verify it on-chain. So in this situation, you would submit the price with your buy or your sell, and if the result of executing those orders at that price didn't change the slope formula, you would know that it was an accurate price. So that's a way to squeeze it into something like the EVM, if that's what you're desiring. Here's some QR codes for sample implementation code on the left, and on the right is a more in-depth article. Yep?
I was wondering about the third one versus the second one.
Mm-hmm.
Oh yeah, that's a good idea. I was wondering what the third, I forget the names of them, the third one versus the second one. And I was wondering if you could talk about what would happen if let's say you have a lot of sell orders and not many buy orders, or vice versa. How does that play out differently, the second one versus the third one? Where does the price end up?
The second one, the smaller amount would just get completely matched at the current exact price, and the other ones would go into like a normal bonding curve. So say you've got more buys than sells. The sells get matched to the buys. That also takes out a portion of the buys, so those are removed. You have this leftover amount of buys, which is executed. They have a total price after the mechanism has occurred. You can combine that with the small amount, which was made at the match, divide that by all the different people, the different portions they had, and they were able to take out a different price total than what this price would be, but it would be rather close, obviously shifted from that amount that went from the buy. With the common clearing price, you would basically share those benefits or drawbacks with the other side. So in that situation, in the second one, those sellers get kind of a better price than the buyers, but that's because there were more buyers than sellers. And in the other one, they would just all share that same sort of average price.
So in a sealed bid mechanism, I can see why batching substantially reduces front running, but given that all of this is open, and given that the proposers can see what would be added to the batch and can delay things to be added or not be added, or if the way in which you're processing the batch is sensitive to the order in which they enter the batch, the validators can manipulate that order. Wouldn't something that gives you an equivalent of a sealed bid be necessary to get the front-running resistance?
So for this, it still wouldn't be necessary, and that's because the order that they come in won't affect the price. And so there's no incentive for someone to, say, be in the same batch. I mean, it might be a separate attack vector, which would be, I would maybe say not an attack, but just sort of like trading on the market, where you see, okay, there's a lot of people moving in this direction right now, maybe I'm going to jump on. And what you're doing is sort of watering down that whole group, but it's not that you have the free riders dilemma. You're not able to guarantee a profit. What you're doing is sort of making an honest judgment and participating in the market.
So there's always, wherever the batch deadline is for closing a batch, the validators are also in a position to take things that are arriving near the deadline and determine whether they're in or out. That also seems manipulable, and manipulating that could also facilitate front running. But the reason I'm raising this is, have you considered a hash commitment scheme that effectively gives you something like a sealed bid auction?
There are, I think, some designs for that. A problem with those is that it becomes difficult to find the clearing price at the end. Everyone is basically dependent on everybody else unlocking their bid before they're able to exit. So that can cause them not, I would say, like a larger attack vector, which is just shitting in the pool.
Okay.
Yeah. How are we doing on time? I have some bonus material about adjustable bonding curves that we can go into, but I was just worried about not having too much time. This is more about the sort of injecting collateral and maybe producing more tokens. Maybe we can actually just open up for more questions, and if it leads to that, I can go back and use those slides as reference. Anybody else have something they'd want to talk about?
Right, so just on the previous question about front running, just wanted to maybe add a comment or continue the discussion about the fact that sure, there's some front running resistance, like you mentioned, by doing batch order collection, but what you open up is say, you have to refine the classification of what constitutes front running. You can get different, like you say, different types of attacks, and of course you have to come up with different ways of avoiding these, such as sealed bid. And there are implementations out there. If you look a little bit into the diffusion project, we've done some research as well on how to avoid these different types of front running that come up when you have a batch off.
Yeah, I mean, I think this speaks to sort of the trilemma that you encounter in so many different situations. Speed, security, price, and I think the DEX and diffusion are great examples where security and what was the second one I just said? Speed, security, and price. Security and price are the most important, but speed is sacrificed with the DEX, basically 6-hour batches. I'm not sure if the diffusion will have similar cycles or not. This makes a similar compromise. I mean, you have an asynchronous purchase at this point. You're not able to do immediately an exchange of the tokens. You have to wait for that span to occur. We're using a single block time on the Aragon one, because the attack vector there is that you could actually block stuff if you wanted to prevent somebody from entering. We were talking about these validators. As long as there's sufficient gossip going on, the validator would have to sort of either control the network or they'd have to control it for enough blocks that it would be extremely expensive for them to do that. Or in a proof of work system, they would have to fill all the blocks with trash transactions for many, many blocks, which would also be very expensive. So if you have a very high security threshold, you might increase that span to much more than a single block. We're currently at very low security threshold, so it's just a single block.
I was wondering, is your Clover project, is that on Cosmos or is it on Ethereum?
It's on Ethereum. It's on the Rinkeby network.
Cool.
Okay. I think that looks like it's it.
Dance moves.